So we are now taking a closer look at how to evaluate classifier. And in order to do so, we will encounter several what are called metrics. So these are, in some sense, KPIs, for classifiers. So let's start with an example. This is something we already have discussed, namely a spam classifier. So let's assume we have a spam classifier, and of course the features of that would be the words that are within the email, but we are not going into the details here. We just look at the outcome of that classifier. So and the classifier predicts the label 1 if it is a spam mail, and predicts the label 0 if it is a regular mail. And our training data also has labels. So the true labels, of course, are also 1 for spam and 0 for regular. So now let's look at the prediction of, I assume that are 10 or so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually we have 10 examples here where we know the true value, the target, and where we have predicted something. So this is these are the targets, the true targets within the training data, and this is what our classifier outputs. So, and if we look at the output, we see the following. For example, here, this here, the first one, that was a spam mail, and the predictor has predicted it as a spam mail. And the second one was also a spam mail, and it's also predicted. Of course, this is something we would like to have. So if we take the next example here, that actually was a spam, but we predicted as a regular. So we missed that. Does anybody of you what the technical term for such kind of situation is? And how that is called? That's a false negative. It's called a false negative. So it's falsely negative predicted. Okay, then we take the next one here. We predict them as spam, but actually it was regular. So that's a false positive here. And the other ones here, they were regular, and they were predicted as regular. So actually this one here, these ones here, the first 2 and the last 5 here, they were okay, and the other ones were not okay. And what is done in order to talk about metrics, classification metrics, there's some vehicle that's called a confusion matrix. That's a very famous name, a very famous concept, a confusion matrix. In this case, we see a confusion matrix for 2 classes. We later on will encounter a confusion matrix for more than 2 classes. But now we confine ourselves on binary classification tasks. So I have repeated here our true and predicted values from the previous slide. And so in this confusion matrix, we have four sections here. And so if we take, for example, this section here, so we have predicted it as a 1, and it was a 1. And that's called a true positive. That is, these are these ones here. These are the true positives. If we take this here, this corner here, we have predicted as, here's a prediction 0, and the true label was a 0. That's called a true negative. So the true negatives and the true positives these are the good things. So these here were the true negatives. But then we have our errors. So for example, we have predicted it as a 0, but it was a 1. Yeah. So prediction 0, and that's called a false negative. And then we have something that is that we have predicted as a 1, but the true label was a 0. Yeah. So this was a false positive, and the false positives are here, these two, as you remember. Yeah. And so this table here clarifies the phrasing a little bit. So if the true label is positive and the predicted label is positive, it's called true positive. And you should not say true positive, but true positive predicted. That makes it a little bit more clearer. Yeah. So, but of course, it always in the literature, and I also do it, we'll call it true positive, but it helps to always say true positive predicted. Yeah. And here, for example, false negative predicted. So we have it falsely predicted as negative. So this is from my experience that is helpful to look at that way here. Okay. So. And what we now can do is we just can count. Yeah, for example, we have 5 true negatives, 5s. We have 2 true positives, 2. We have 1 false negative, and we have 2 false positives. So this is our confusion matrix, and this is something that is the basis for the calculation of our matrix. And the first one is, of course, accuracy. And accuracy is quite simple. Yeah, if you look at it here, we have, so accuracy is the fraction of things we have done right, yeah, with respect to all things. So this is our confusion matrix here. So what are the things that have been done right? These are the true positives, the true negatives, and the true positives. Yeah. So these are 5 plus 2, true positives plus 2 negatives, 5 plus 2 plus 5, or 5 plus 2, doesn't matter. And we have taken the overall, all of them. Yeah. So if we look at it, we have 10 examples, and 7 of them are okay. We got an accuracy of 70%. Yeah, so that's quite simple. So it's a fraction of correct predictions among all predictions. But now paraphrased here by means of a confusion matrix. Yeah, the reason why we take this vehicle here is because there are other matrices we will encounter soon, and there it helps to have the confusion matrix. For accuracy, it would not be necessary, can calculate it directly. Yeah. So why are there other matrices? And please look at that example here. And yeah, maybe some of you is able or can paraphrase what is going on here. Why is that problematic here, what we have?
Actually, classifier is defective because it is always predicting 0.
Yeah.
Just luck by chance, it is like inputs are mostly zeros, so we are not able to identify the defects.
Yeah. Yeah, the classifier is useless, of course. But look at the confusion matrix. Since 9 of the 10s are here negative, and we have 9 true negatives, yeah, 9 of the 10 have been predicted correctly. So this classifier has 90% accuracy. Yeah. So let's assume you have persons and you would like to predict a specific kind of cancer. when you predict has not cancer, and only one of 100,000 people has that cancer, yeah, you have an enormous accuracy, of course, but your classifier would be useless. Yeah. Do you see the point?
Yes.
That, yeah. That's so. What do you think? What is the reason that this is that we have a useless classifier that nevertheless has a very good accuracy? What is the reason for that?
Inputs are all negative, mostly negative. That's why we are not able to whether
Yeah.
classify is good is or not. So test data is not good, we can say.
Yeah. So the point is we have what is called an imbalanced data set, since the positive cases are rare, and for cancer and so these are rare. Yeah. And that's the reason why accuracy would not be a good matrix here. Yeah. So if we look back at our digit example, why was accuracy there okay, a good measurement?
Our input was more diverse there.
Not why the input was more diverse, but that's not the reason. Yeah. That we what was the reason? The data set was balanced. The number of zeros and the number of ones and so on, they were they were distributed evenly. Yeah. And therefore accuracy is a sensible metrics there. Yeah. If we would have in 99%, we would have the digit 1. Yeah. Then we would have an imbalanced data set, and then accuracy would not be good. Yeah. Okay. So accuracy sometimes might not be the right thing, as you see. Yeah. So then, of course, what might be a sensible metrics for classification in such cases? And of course, we encounter these kind of cases. And there are two things that are available there. And the one is called recall. Recall is true. It's called the true positive rate. So recall is just take the true positives, yeah, among all positives. So so if we look here at the confusion matrix, yeah, so all those that have a true label 1, so these are the positives. These are the actual positives here. And the recall tells us how many of those have been truly predicted as positive. And that were 2 here in that case. Yeah. So we don't take the whole confusion matrix, but we take only the positives and take the fraction of which one we have predicted correctly. And so we got a recall here in that case of 66%. What would be the recall for this year? How many were positive?
1.
And how many we have predicted as being positive?
0.
Yeah. And taking the true positives are 0 in that case. Yeah. Divided by 1 delivers 0. So the recall would be 0. And you can see it immediately here. There's one instance here, and we don't get it with our predictions. So we're not able to predict anyone. We do not find out anyone. So our recall, our true positive rate, or our hit rate, we could also call it hit rate, is 0 for the classifier here. Yeah. So that much better tells something about that useless classifier. Yeah. So that's the recall. Yeah, it's true positive rate or hit rate. How many you really hit? Yeah. So the fraction of true positive predicted to all positives. In this case, 2 of 3. Yeah. That's the recall. The next thing is called precision. So what is precision? Precision now looks at all the predicted ones. So it's a fraction of true positive predicted to all positive predicted. So now we take all positive predicted. This is this here. Yeah, this is that column here. Before, for recall, we have taken all those that have a true label of 1. Now we look at all that have a that have been predicted as 1. Yeah, and if you look at it, so how many do we have predicted as 1? So that what were the true positives? No, how many we have predicted as 1? Sorry, first of all, these are, this one has predicted as 1, this has predicted as 1, this has predicted as 1, and that has predicted as 1. Yeah, so all that we have predicted is 1 that were 4. And among those that we have predicted as 1, only 2 were truly predicted as 1. Yeah, so we take the true positives with respect to all that have been predicted. So these are the true positives, and the false positive predictors, they are also predicted as positive, but of course falsely. And therefore we have a precision here of 50%. Yeah, so that would be the precision here. So if we take a look at here at our example here, what is the precision of that?
Precision is also 0.
It's also 0.
Positives are 0.
It's also 0, yeah, because we don't have any as positive predicted. Yeah. Okay. So now these are the two measures. So how many hits do we have? How many our classifier is able to find instances? And on the other hand, for example, if we take all one we predicted as all positive, yeah, then we get a good recall, but our precision would suffer, of course. And this is something that is discussed here. So, so now we have 2 measures. Actually, we have 3 measures. We have the accuracy, but this is something that is not so useful if we have imbalanced data set. And we have precision and recall. They are much better for to cater for this imbalance. And if we look at recall in context of precision, if we take the both together, actually it's easy to get a high recall if we just predict anything as positive. Yeah, of course, then we have then we get all our real positives. We just say it's true, and then we get all the ones that are really true. Yeah, but the precision would be very bad because we would have many of them that were not true. Yeah, so if again we take our example here and we would predict everyone as 1, yeah, then we would have only 1 true positives, yeah, and many false positive predicted, yeah, and therefore our precision, we would have 1 by 10. Our precision would only be 10% here. Yeah, so so only relying on recall, that could also give a wrong impression of the classifier. The other way around it, we can do the same. We can get in high precision. Let's assume we predict only one example as positive where we are really sure that it is positive, where the sign and the features definitely tell us that must be a positive one, and all other ones are classified as false. Yeah, then we would have a very good precision that would be even 100%, because among those that we have predicted as positives, this single one, it is positive. So we get a precision of 100%, and but the recall would be bad. So only taking precision would also not be the best option. So then we might have then an easy solution, or a first idea that might come into mind is just calculate the mean between recall and precision. That might be a good idea, and actually that's a good idea. Yeah, take both of them into account. But there's something. The first thing that we might do is we calculate what the usual mean, that is the arithmetic mean. Yeah, but actually the arithmetic mean is not a good choice, and a better choice is what is called the harmonic mean. Yeah, and that's what is called the F1 value. Yeah, so the F1 value, and this is the formula for the harmonic mean here. Yeah, that is usually the metrics that we are going to use. Yeah, so just to give you an idea why the arithmetic mean is not the best option. Yeah, so let's assume our classifier has a precision of 1. Yeah, and we have, for example, a recall of 20%. Then our arithmetic mean, this is the arithmetic mean here, this blue line, would give an F1 value of roughly 50% or so. Yeah, even though the recall is only 20%. Yeah, so this would lead us, that would give us the impression that the F1 value of 50% would be quite okay. Yeah, even though it actually is quite bad. Yeah, and the harmonic mean here, in that case, if we have only a recall of 20%, would only give us about 30%. Yeah, so this is the line here for the arithmetic mean, and this is for the for the harmonic mean. Yeah, and by these diagrams here, we can see that the harmonic mean is much more a better description of the fitness or the goodness of our F1 value. Yeah. Okay, so this was the case F1. So now we have accuracy, we have recall, and we have precision, and we have F1 as usually something that is reported by a classifier. Yeah. Okay, so this is this. Now we have this matrix, and now we can often classifiers do not tell us it's true or it's false, but usually classifier give us what is called scores. They tell us how sure, how confident they are for a specific case. Yeah, if it is a positive or it's a negative. And in order to discuss classifier with scores, I would introduce another number here, namely the false positive rate. So the true positive rate, yeah, these is the hit rate. This was a recall. So how many do we hit of the real cases? And the false positive rate tells us how many false alarms we are emitting. Yeah, and of course, false alarms are not what we would like to have. So how is the false positive rate defined? It's just the false positives. This is this one here, with respect to all with respect to all negatives. This one here. These are all the negatives. These are the false, those that are falsely declared as being positive. These are the false alarms, and these are all the negatives. And if we take the fraction of the false alarms with respect to all negatives, we get our false positive rate or alarm rate, or however we would like to call it. Yeah. In this case, 2 of 7 have been falsely declared as being positive. So we have a false alarm rate here of 29%. Yeah. So the discussion that is following, that is concentrating on this true positive rate and this false positive rate. So let's recapitulate. The true positive rate, this is take those that have been predicted as positives among all the positives. Yeah. And the false positive rate is take all those that have been predicted as positive, but are actually negative. So we take the fraction among all the negatives. Okay, so now let's talk about a classifier that delivers us scores. So if we look at the first row here, these are our true values. Yeah. So these are our here from our training data, the true values. And now let's assume we have a classifier that not tells us if it is a 1 or 0. So if we look back here, this was a classifier that just tells me this is 1, this is 1, this is 0, and so on. But a classifier that delivers scores not just tells us 1 or 0, but is a little bit more, has a little bit more detail. Actually, it tells us how confident it is. It tells us a score, and this gives us some kind of confidence. For example, for this one here, for that case here, it tells us, okay, I only assume 10% that it is positive. And for this, I tell you, the classifier tells you he's this 37%, yeah, and so on. So, for example, for this one here, it gets a score of 0.9, yeah. So it's quite confident that it is a 1. So having these scores, how do we turn it into a classifier? The way we would do it is we decide on some kind of threshold value for our scores, until which we say it's a 1 or it's a 0. So let's take this threshold here of 50%. That might be the most natural one that you might encounter. So if I say, okay, if the score is greater equal 0.5, I will say it will be a 1. Otherwise, I will say it is a 0. Yeah. So you see here, I take all those that are below 0.5 and give them a 0 as a prediction, and for all the other ones, I get the 1 for the prediction. Yeah. So having taken that threshold, I get my predictions here. So I get a classifier. Oops. I get a classifier that looks like this. But I can also adjust my threshold. Yeah. So if I find that with respect to precision and recall, this threshold might not be the best threshold, I might use a different threshold. For example, if I say everything that's greater equal than 0 as a score, I predict as 1, yeah. So I get this useless of course, here that always predicted as 1. Yeah. If I tell everything that's only give it a 1 if it is greater than equal than 100% here as a score, everything's get a 0. Yeah. And in between I get some different predictors here. Yeah. And so if I have a classifier that delivers as a score, I can define some kind of threshold, and there, depending on that threshold, I get the real prediction, 0 or 1. Yeah. And what could be done now is I can take all these thresholds and calculate the true positive rate and the false positive rate. Yeah. So the hit rate and the false alarm rate. Yeah. So for example, if I take this first row here, only if I tell you if it is greater or equal than 0, than 1, and I assign it, I predict it as 1. So the prediction will all be zeros. I get that confusion matrix here, and I get a false positive rate of 0 and a true positive rate of 0. If I take a threshold of 0.8, the first two will be predicted as 1, and the other ones will be predicted as 0. So I get a false positive rate again from of 0, but a true positive rate of 40% now. So, and as I go along here, my threshold will be lower and lower. Yeah, I get different false positive rates and true positive rates. Yeah, and the last one, for example, gets me a false positive rate of 1. Yeah, and a true positive rate also of 1. And if I take these points here, the different points here, 0, 0, this is this point here, 0.4, this is that point here, and then 0.2, 0.4, 0.2, 0.8, and so on. If I calculate all these, I take all these values here and draw them here in a chart here, where the x-axis is the false positive rate and the y-axis is the true positive rate. I get that curve here, and that is called a ROC curve, a receiver operating characteristics curve. Yeah, and what I can do is I can calculate this area under the curve, and this is the next measure that classifiers have. So often for classifiers that have scores, the AUG value, the area under curve, is calculated. Yeah, and this is a further notion here, a further matrix. And let's assume we have an optimal classifier. So what is an optimal classifier? So an optimal classifier is where the thresholds separates truths and falses. So let's assume here I have these values here, and I have these thresholds here. And you see, if I take a threshold above, if I say everything above 0.55, sorry, everything above 0.5, I declare as 1, and everything below I declare 0. Then you see it doesn't make any error, because all those here will be predicted as 1s, all those will be predicted as 0s. Yeah, and then we get a ROC curve that looks like that here, and this is an AUG value of 1. Yeah, if you look back here at this one here, you see here, for example, if I take 0.5 here, there is one that has a score of 0.7, but nevertheless is negative. Yeah, so we don't have a threshold that really, so only this threshold here 0.75. Yeah, that would distinguish then. But it would also not be okay because below we would have some ones. Yeah, the optimal classifier would look like that. If we take the sorting here of the scores, then we also get the sorting here according to the ones and then zeros. So first all ones and then all zeros. Yeah, and you see here, it's not the case. Here we have a 1. Yeah, it's not sorted. So that would be an optimal classifier. In practice, of course, we don't have them. Yeah, and actually, it doesn't matter if for example, if it looks like this here. Yeah, if we would another example that would be like this one here, we nevertheless would find here a threshold where we can distinguish the truth and the false values. Yeah, that would be the optimal classifier here, and if we take a random classifier, so we just flip a coin, we just guess if it is true or if it is false. Yeah, then we get a ROC curve here that looks like those ones here. Yeah, and you see the ORC values would be roughly about 0.5. Yeah, so an ORC value roughly on 0.5, yeah, would be a random classifier. So the optimal classifier would be with an ORC value of 1. The random classifier would be with an ORC value of 0.5 roughly. Yeah, and between those values we would have our real classifiers. Yeah, and the larger the value, the better, of course, the classifier is. Yeah. So in this slide I have provided, I have done some kind of simulations here. Yeah, since we have already spent some time here, I'm not talking about the details here. Maybe you can later on take a look at it and maybe you figure out what I have done here. Yeah, the idea behind is that I have calculated random numbers, so that was random guesses, and I looked at the ORC curves. Yeah, and I've done that for 4 times in order to show you that we always get a classifier with roughly 0.5. Okay, so these were binary classification problems. And last but not least, I would like to talk about classifiers with more than 2 classes. How we could deal with them. Yeah. So let's assume we have a classifier for newspaper articles. And let's assume we have 3 classes, namely, this is a business article or an article on politics or an article on sports. Yeah. So this classifier now has 3 classes here. And what we can do is we can also draw a confusion matrix. Let's assume these are our true values. So this article number 1 was politics, number 2 was also politics, number 3 was sports, and so on. And we have predicted them as follows. Yeah, for example, the first one that was politics, we have predicted them as politics. The second one was politics, but we have predicted them as sports, and so on. Yeah, so then also we can draw a confusion matrix. Yeah, but now we have 3 labels here, not only 0 and 1. Yeah, so and then we can, for example, calculate all those that were sports and that have been predicted as sports. So if we take all those that have been sports, these were the 3 ones here, as you see. And among those 3, we have 2 of them we have predicted as sport. Yeah. So you see we have 3 ones that are sports and 2 we have predicted as sport and 1 we have predicted as politics. So this was a sports article and we have predicted it as politics. Yeah. And so taking all the different values here, yeah. So for example, if we take those that were business, and none of the business has been predicted as politics, as you see. Let's see. So there were 3 that were business, Two of them we have predicted as business, and one of them we have predicted as sport, but none we have predicted as politics. Yeah, this is a 0 here and that. And so that is taking all the cells here, you can figure out why they have the corresponding value. Yeah. And also here we can talk about accuracy, precision recall, and F1. So if we take the accuracy here, the accuracy is just take all correctly classifies divided by all. So these were predicted as business and were business. This were predicted as politics and were politics. And this were predicted as sports and were sports. So the diagonal, if I add everything in the diagonal, I get those that have been predicted correctly. So that were here a 6. Yeah. And overall I have 9. Yeah. So I have 6 by 9 accuracy, so 66% were the accuracy here. Yeah. So regarding precision recall, I can now figure out for each class how the precision and the recall is. So for example, I take business. So I take this row here. I take business. So how many records are there in business? There are 4. Yeah. And how many of them I have here calculated correctly here? These were 3 of the 4. Yeah. So I have a recall of 75%. The precision here is 1 because among all those that I have here predicted as business, so this one, that one, those 3, yeah, all of those are actually business. Yeah. So so the true positives with respect to all that I have predicted as business is the same. So I get a precision of 1 here, and therefore I get for the class business an F1 value of 85% and so on. Yeah. And so I get a per class recall and precision value here. But what I also can do is I can summarize that. So for example, I can calculate the overall precision and recall and the overall value. So for example, I just can take the mean of all of the 3 classes here. That would be the macro. Or I can take the weighted. So I take the F1 value and take the support of 4 into account. I weight it according to the number of cases here. So for example, the weighted average would be F1 value would be 68 here in that case, and the macro would be 64%. Yeah. Which one is the better depends on your use case. Yeah. So if you encounter a classifier and it has been reported, this classifier had that accuracy and that F1 value, you now should have an idea what is meant by that. Yeah. And if you have more than 2 classes, you might get a per class precision recall accuracy, or you might have an overall, and that might be a macro averaged or, for example, a weighted average. Yeah. Okay. So that's about how we can evaluate classifiers. So let me stop the recording here.